Okay, everyone, welcome back. So today we're going to have a presentation by some of the TAs. If you don't know yet, this is David, one of the students working in my group, who's helping as a TA in the course, and Chanakya is the other TA. Chanakya will also be presenting later in this lecture. And so make sure you get familiar with their faces because they're going to be having office hours, they're going to be helping you with your projects, they're going to be moderating all the readings and discussions. So before they get started, there's a couple of logistical things. First of all, make sure you submitted your project proposal, project fee proposal. So there's a short form where you fill in your teammates and your preferences. I've shared the responses with everybody on Piazza. So if you don't have team members yet and you're looking to form a team, use that spreadsheet to maybe reach out to people who have similar areas of interest. Okay. And the first assignment is that next Thursday, we'll be having project proposal presentations. So by then you should have formed your team, decided on an idea, and it's basically a 5-minute presentation per group to just quickly run through what you want to work on, what ideas, what data sets you're going to use, and to get a feedback from the course. So those instructions are on Piazza, exact grading instructions for that proposal presentation, and the following week, you're going to submit a short report for that proposal. So just the text version of that so that we can grade and get feedback. Okay, so remember to fill in that form to help look for teammates and also to start working on the project proposal presentation and report. Okay, so David and Chanakya today, we're gonna tell us some tutorials on practical tips for PyTorch, Huggingface, building, iterating, and debugging your ML models. Go ahead.
All right, thanks Paul for the introduction. So I'm David, I'm the TA for this course. And we're going to first cover how to use PyTorch and then talking about how to fine-tune a very simple large language model on Huggingface. And before we get started, please open these two links and you should see like two collab pages and you can follow along as I work on these collabs. So the tutorial today aims to get you started with the PyTorch. So if you already know PyTorch, then this tutorial may not be that useful for you, but I aim to structure this so that everyone will at least know a little bit more, hopefully. So let's get started with PyTorch. Is everyone able to open this collab? Okay. Good. So first, very brief introduction into PyTorch. So PyTorch is a library that helps accelerate machine learning processes. So the central piece of the PyTorch is tensor. Tensor is just like a bunch of matrices that you learn in linear algebra. And well, first we need to import the PyTorch. And let's first go through some of the simple operations on PyTorch. First, you can initialize a tensor in several different ways. First, if you have a 2D array of like 1, 2, 3, 4, you can just call like torch.tensor data to initialize a tensor of that particular data. And if you have worked with NumPy array before, you can, of course, convert the NumPy array into a torch tensor using the torch.from NumPy command.
Excuse me, could you pull up the slide with the URLs again?
Yeah, sure.
Or maybe I write one.
So there is in the slides, so if we copy the slide and then that's good enough. I still say it works.
The slides. Oh, yes. Yeah, you can also visit the slide page here. which contains the URL as well.
Links are here.
I'm just going to quickly go through this part because that's some basic stuff that's not very like relevant. Okay. And then we can initialize a tensor of a particular shape. If we want 2x3 matrices, we can initialize a tensor using the torch.rand. This is a command for initializing a random tensor, and then torch.ones, torch.zeros to initialize a tensor of particular shape of like ones and zeros. And one important thing about the tensor is that they have different types. So you can call the tensor.d type to see the types of the tensor. And one common source of bug when you deal with like machine learning models is that the type of tensor is not the type you intended it to be. So if you initialize a tensor of like an integer type, you cannot like multiply it with a float type and then like put the result back into the integer type because that's not compatible. So make sure when you load the data, you check the tensor type using the tensor.d type. You can just use print, or if you're familiar with debugger, you can use the debugger to check the type of each tensor. And because PyTorch is like a machine learning library, the tensor can be used on like multiple devices, namely like the CPU and the GPU. And you can also use the tensor.device to check the device of the tensor, and that's also a very common source of error. For example, you have a tensor of on different devices, one on CPU, one on GPU, you cannot multiply them together. So you need to use some command called like tensor to device to move the tensor to the device you want it to compute. And then, of course, we have some very simple operations on tensors. For example, if we have two tensors called x and y, you can use x plus y to add them together. And one thing to note, though, like the x times y here, this is not the matrix. A matrix is multiplication, This is actually the element-wise multiplication. So if you come from like a more of a MATLAB background, you may know like x times y is like matrix multiplication. This is not the case in PyTorch. If you actually want matrix multiplication, you use this one, torch.mm. And that's the common like row times column add together, that kind of matrix multiplication. So that's just a very brief overview of the torch operations. Here I'm going to go through like a complete small projects using the smell data we collected in our lab. So in our lab, we actually have a small like smell sensor or some like a bunch of gas sensors that collects smell data from a particular like substance. And I think it would be nice if you can use this like very simple data to build a small project in this tutorial to walk you through the entire process of like training, data processing, evaluation, all that kind of stuff. So before we dive into the model, we first need to look at the data. And that's something I strongly suggest. Like the data may not be in the format you intended it to be. And that's very common in both like the data you collected and the data downloaded from the internet. So from my experience, it's very common that like on the documentation page, the data has like this format, but after you download the data set, it has another format or something. So it's very important to actually look at the data before you do any modeling and maybe like training on that kind of data. So here let's run this cell to download the smell data we have collected. And then we'll download a bunch, import a bunch of libraries. And for this project, we are doing like a three-way classification of like 3 smells, which are ambient, alcohol, and coffee beans. And then let's run this cell to load a bunch of like data paths. So if you look at the this folder page, if you open the folder, open the smell sensor, smell data switch, you'll see a bunch of like CSV files that correspond to each of the categories. We have more categories, but for this simple tutorial, we're going to only use like 3, which are like ambient, alcohol, and coffee beans. And then here we use the os.git directory to list all the files here. And then we open a file to see how it looks like. So it's very important to look at the data. And from the data here, you will see like we have a bunch of columns which correspond to each of the like particular like gas sensors, and then to situation, pH, VOC, that kind of stuff. And I also think it's very important to actually visualize the data. If you are working with like time series data, visualization is very important because you will see like which data are kind of like relevant to the category and which are not that relevant. So as you can see here, so this is for the alcohol detection. And this is like the rating of like each of the gas sensors. And the red region here is the actual rating of the sensor. So what we did is that we first collect some like ambient readings in this like white region, and then we move the substance close to the gas sensor to collect the actual reading of that particular substance. So this way we can like eliminate the effect of like ambient factors, which are we found to be like very useful for this particular project. So as you can see here, some of the gas sensors are very like sensitive to the substance. And for example, like the NO2, VOC, this kind of thing. And some other stuff are not very relevant. For example, the alcohol sensor, I think it's not working. And also we have something like temperature readings, pressure readings. These are not very related. Yes.
For the state, was that just something you were manually collecting, or like how is that data actually collected?
Yeah, we have like Python script to automatically like switch between state equals 1 and state equals 0. So not automatically like
It was like, so like where you were like having some robot arm or something, moving it closer and further, and that's what state equals 1, state equals 0.
that's
Human arm.
human arm.
Okay, so like on a screen you have 0 and 1. Human sees 1 is like, I'm gonna
Move it
move it
there.
closer. Okay.
Okay, so then move it away.
That's right.
Of course, robot arm will be great.
Human seems good too.
Yeah, I wish we could have some robot arms. So you will see some channels are relevant to the substance and some are not. So the question here is like, should we just eliminate this column or should we actually include this in our training? So my suggestion is very likely, like most of the time, you should not need to eliminate any channels, because if the channel is irrelevant to any of the categories, the neural network will automatically learn that, and after the training, the neural network should ignore this channel like automatically. So but these are like something you could keep in mind. If the neural network like doesn't work at all, maybe you should try like removing some of the channels, but most of the time this is not needed.
So David, if you know the sensor is not working, why do you still include that?
I think this sensor is not working in this particular sample. It was working in some other samples. So yeah, so if you do want to you remove a channel, you should look at like all the data instead of like just this one file.
So basically, featuring the array is not necessary in the training.
Yeah, I feel like neural networks are usually like very robust to noise in one like particular channel. If the noise are like spread across like different channels, that may be a bit too difficult. And then we need some kind of like PCA to should I explain it? To remove some of the noise. But for this one, you can actually see that this data is actually pretty clean, so you don't need any kind of like pre-processing to fix that. But we did take the average of like each period and subtract that with ambient gradient, because like we found that the ambient gradient is actually the initial gradient of each sensor is actually a very variable, like it's stochastic from session to sessions. So we subtract the actual radians from the ambient radians to get a relative change, so that the data is like better.
That's in your sample or like when you are doing it?
And this is a part of the pre-processing, so it's not a part of like data collection process. And then another thing we found is that like the range of each readings are a lot different. Like for LPP, we have like a range between like 0 to 2000, but for a lot of other things, for example, the NO2 is like 60 to 100. So this tells us one thing is that like we need to do some kind of normalization. So this is actually one of the most important pre-processing you'll need to do, because the neural networks are not that robust to the range change. So if you have a column, a channel that's like 2000, very likely this column, this channel will dominate the entire like training process. So as you can see here, after we load the model, load the data, combine the data, split the features and labels, we'll need some like normalization. So here we use the standard scalar. This is from the scikit-learn package. We use this to transform the X, the input data, to a range, I think it's 0 to 1. So that it's more like robust. And then we use data splitting of like 8% versus 20%. We use 8% as training, 20% as testing. And then we initialize the data set and the data loader. So if you are not familiar with these terms, the data loader, the data set actually gives you the data. And the data loader is a loader from like the PyTorch that initialize a multiple like worker process, which speeds up the data loading process through like parallel processing, and then it gives you data a batch of a time. Like each time you ask for the data, it gives you like 16 samples instead of one sample. So the benefit of this kind of processing process is that like if you work with like multiple samples at a time, the gradient, the model calculates, which is like how to update the model to make it better. The gradient will be like more robust because that's the average across like different samples. So another like practical tip is that when you train the model, make sure you use the as large batch size as possible that can fit on like one GPU so that the training process is the most like robust. And finally, we can design our model. This is just like a very simple like MLP model, which we stack like multiple linear layers and batch norm and random activation. So these are like very simple models that we can adjust here. If we run this cell, you can adjust the layer sizes here. We have an input size of 13 and output size of 3 because we are doing like three-way classification. So these two numbers you cannot change, but anything in the middle you can change it to like other values or make it larger or make it smaller. So usually like for our simple data, we just need maybe 2 or 3 layers and that should be enough. Yes.
Good question. So how do you decide the number of layers and the size for each layer? Is it still heuristic or that's very good?
I think the good starting point is that you start simple. Like you just use maybe 2 or 3 layers and see how you perform. And we have a lot of like how to debug your model tutorial afterwards. So maybe we can discuss more in detail about that later. And then we have a training loop here. I don't think I have time to go through all these lines, but essentially that like you get the data, the label from the data loader, and you feed the data into the model, and you compare the model's output with the ideal output to get a loss. And the loss, after you get the loss, you calculate the gradient, which tells you how to update the parameter to make the model better. And then finally, you call the optimizer.step to actually make the model better. And that's the entire like what this says. Okay. And after the training, we can run the evaluation, which is very similar to training. You just feed the data into the model, but this time we compare the model output with the ideal output, and we just don't update the model anymore. And as you can see, we got an accuracy of like 75%, which should be which is kind of okay. And then we can also see like the more precise breakdown of like each of the categories. You can see like the model has a pretty high like precision, recall and F1 score on like ambient and alcohol, but the model doesn't work so well in like recognizing the coffee beans. And after you done this, you can improve model like iteratively. The way you do that is that you first identify like which category performs the best and which one performs the worst. And for the ones perform the worst, you can see like, is it because that we don't have enough data, or is it because some other things? And if we don't have enough data, maybe we can collect like more examples from the coffee beans, and that's how you can improve the model later. And finally, don't forget to save the models so that you can use them for like further analysis later on. So this is for the PyTorch tutorial for like training a very simple model. I know I skipped a lot of things, but if you have any questions, now the good time to ask. Yes.
Time series, what is the row that we're classifying? Is it a full time series or is it just like a sample from that?
Yeah, good question. I think we sampled a bunch of periods. I think one period is like 10 timestamps, like 10 rows. And we like segment the entire like reading into this different like elements, and then we do the classification.
And the classification, it's on one of those segments then of like 10 something or?
Yeah.
But these are probably design decisions that are super important in your application, right? What is the window, bigger, smaller, and what's the label with respect to each window? And I think David also skipped through how you should split your train and test data. That can also be very important, right? Because
Yeah.
you, for example, split your train and test data such that they were from the same day or within the same hour of collecting a sample, then it could basically just memorize the sample without actually generalizing to when you want to apply the sensor in a future day. A lot of these hyperparameters in machine learning are things that you probably have to decide and design very carefully.
Yeah. So that's actually a pretty good question. So when we do the train test split, we want them to be as like close to the real life scenarios as possible. So if you are going to like train the model on one day and use the model on another day, then the train test split should be exactly like that. So you shouldn't use like maybe the first part of a session for training and the other part of the session for testing. That's not the model will perform maybe pretty well, but that's not that will not translate to the real life performance.
One other example is that we did some data collection in one of the rooms that we have in our lab space, and we trained a model, but it wouldn't work in some other room or outdoors because it basically wasn't able to learn how to differentiate between different ambient factors like temperature, humidity, and so on. So that means if you train on something and test somewhere else, make sure you collect both sources of data and split the data accordingly.
Yes. So I'm also going to very quickly go through model classification with the random forest. So random forest is not like a deep learning model. It's a very simple model that you have a bunch of like decision trees, and you use majority voting to combine the output of each like decision tree. So this training should also be very fast. We do a train test split, and we just initialize a random forest classifier. This is also from the scikit-learn package, and then we can evaluate it here. And then we get accuracy of like 95.8%, which is actually a lot higher than the deep learning models. So this also tells us like for very simple and non-noisy data, sometimes a simple model, a shallow like random forest classifier will actually perform much better than the fancy deep models we have constructed. So another practical tip I have is that when you deal with data that's like low dimensional, like each data point is like a couple hundred like numbers, very likely the model that will perform the best are like shallow models like random forest or like SVM, that kind of things. So we'll deal with like that kind of data. I suggest you to start with very simple like shallow models before moving to deep models. Yes.
So with this statement of like, oh, we're like testing it in different rooms and getting like different results, is the random forest like robust to that, or like is like that adding kind of like another?
But that I'm not quite sure. So I don't think we have test data from another room yet. At least it's not in this GitHub repo. So but in general, I think a simpler model is more robust to noise. Because like a more complex model, it has a very like complex decision boundary, and it's more like more likely to overfit on the noise of the training data, so that it's not like that robust to environmental change or something.
Yeah, but to answer majority of question, none of the models work very well yet. If you go to different locations and then you outdoors.
Yeah.
Sure.
Yeah, this is when like you don't have enough data to work on that. So if you have like the vision data sets, because where you have like very powerful vision encoders, it will likely work on like any of the data you have. But if you have like time series data, so this is not very like generalizable to other domains. So very likely you have a very simple model that works under like one environment, but doesn't work so well in another environment. So this is for the PyTorch tutorial. Let's quickly go through the Huggingface tutorial before we dive into the how to debug the model. So the Huggingface, you may know Huggingface, but Huggingface is actually not a single package. It's a set of packages that allows you to train larger models with less code. So it has two main like sub packages, which are transformers and datasets. Yes, they are called that. And transformers provides API to initialize large models with pre-trained weights. So if you work with like large language models, you use the transformer package to initialize the pre-trained model. And the data set is for you to like easily download public data sets from the internet. So you may ask like, how do I choose the models or the data sets? Well, you can actually search online on the Huggingface website and see like which models are popular for your use cases. And you can just pick one and plug in the name in your code, and you should be good to go. And there are also some packages that's not from Huggingface, but it's very popular because it makes the training more efficient, which are like bit and bytes. This provides function to quantize a large model to make it smaller and fit better in your like GPU memory. And another thing is the flash attention. The flash attention package makes the training process faster and then with less memory. Okay, so they're pretty much the same, but yeah. And for this tutorial, we'll train a large language model with LoRa. So the LoRa is basically an adapter to train a large language model with less trainable parameters so that you can train it with less memory. Okay, so let's go to the Huggingface tutorial. Where is it? Okay, here. Is everyone able to open this collab? Okay, nice. So before we use the model, we actually need to log into Huggingface using this like notebook.login. I have too many sessions. Okay. Let's see. Oh. Okay, interesting. I only have one session. That's too many. Okay. And before you run any of these cells, make sure you select the change runtime type and select the GPU here. I actually don't think we have time to complete the entire tutorial because the training will be pretty like time consuming, but we'll at least go to the training part. So after you click this cell, you'll see like this web page that asks you to input your Huggingface tokens. And if you open your like Huggingface page, you can initialize create a new token here. Make sure you select the right if you want to publish your model actually on Huggingface. And then we can give the model a name, for example, like Colab, and then click create token. And then we can copy and paste the token here to log in. So the reason why we want to log in is that like the model we use is actually have a gated access. So if you open this page on the Colab, like the big code, start coder base 1B, you actually see like a diagram about like applying for access to the model. So here I already have the access to the model, but if you haven't gotten access, you'll need to like agree to their agreement and click maybe apply for access, and then it should give you access automatically. And then we want to install a bunch of packages. These are mostly the one we talked about, which are from the Huggingface. And while it's doing that, let me go through a bunch of the parameters here. So here on the first line, you'll see our model name, dataset name, and the dataset column, which are about like which data we want. So we're using a model called star code base 1B. This is a 1 billion parameter model. So the GPU we are using is the it's called T4 from NVIDIA. It has like a 4 gigabytes memory. So the way to determine like what kind of model you can fit on your GPU is to look at this number, the final number here. If you have like 1B model, it's very likely that it will fit on a 4 gigabyte GPU. So I think the rule of thumb is that you multiply the number before the B here by 2, and that's the rough minimum memory you will need to run the training process. So if it's like 1B, you need at least 2 gigabytes of GPU memory if you want to train the model. Actually, that's for like inferencing on the model. For training, you will likely need a bit more memory, but that depends on the process, like how you want to train it. And we have a bunch of parameters about LoRa. So the LoRa here, you'll see a bunch of parameters, and this basically like determines how much you want to modify the model. So the larger this R and alpha is, the more memory you will need, and the larger the modification will be. Okay, I think that's done. And we can load the data set using like this one line. For this tutorial, we are only going to take like 4,000 samples because we don't really have enough time to do it. And then we will initialize a tokenizer. So if you don't know how what tokenizer is, it basically like translates the English words into tokens that LLMs can understand. So if you are working with large language models, very likely you will need to deal with the tokenizer. But that's actually pretty simple. You just call the, where is that? Yeah, we also have some kind of like FIM transformations. These are not very important because I don't think people use it anymore. So I can skip that. And then we define the data set. So the data set is something that defines how the model how the training process should extract the data from the raw data set. So that one is already done. I think the only thing I need to mention here is that you need to call the tokenizer here to convert the words into tokens. So this is something that you don't need to do for like traditional models, but you do need to do for each of the large language model tuning. And then we can load the models when you run this style. And right now we are loading the model in 4-bit because of the memory requirement. Ideally, I think you should load the model in 16-bit if you want a pretty like stable training process, because 4-bit is not that stable. But for this tutorial, we're using 4-bit because that's the only thing, that's the only size we can fit into the Colab GPU. And then we'll set up the LoRa and train the model. Okay, that one is still running. And one thing nice about the Huggingface is that it has a very nice like integration with 1DB. 1DB is like a training monitoring tool that tells you like how the training process goes. So when you run this training now, you'll see this thing from like 1DB. And if you open the 1DB .ai/authorize page, and then you sign in with your like 1DB account, you can copy and paste the API key from 1DB to this training run. And then you can actually see the training run live on this like web page, which is great. If we wait a few seconds, I think it will show a bunch of things we care about. So before they log in any like training loss or like evaluation loss, one thing I tend to look at for each training run, these two panels, which are like GPU memory allocated and the GPU power usage. So these are two important indicators. And GPU memory allocated is for like how much GPU memory are you using for this training run. So the if the GPU memory allocated is like too large, for example, like 95%, it's actually very likely that your training will like have out of memory error later on in the training process. But if the GPU memory is too low, it means that you have too small like batch size, and the training process is not that ideal. So my suggestion is to, if you are working with like large language models, my suggestion is to like keep the GPU memory allocated at around like 80 to 90%, so that it's less likely that you will have like out of memory error, and also you are utilizing most of the memory available for your GPU. And another thing I tend to look at is the GPU power usage. So this one tells you like how busy your GPU is during this like training run. So if the GPU power usage is like 10%, very likely that like your training pipeline or the data processing pipeline is not very efficient, and your GPU is like idle most of the time. So I would say for this one, GPU power usage larger than like maybe 60%, is kind of ideal. If it's like less than 60%, you may want to check your data set implementation, processing script, and the training pipeline to see like which parts are very slow. So this is for the Huggingface. I don't think I can finish this training run in this class. So like, but do you have any questions?
Can you also cover, we go to weights and biases, the other things that they could look at beyond just GPU usage?
You mean the loss?
Yeah.
I don't think it's logging the loss yet. Oh, it had loss. Okay, but what just for one step. Okay, the loss is also very important. You want the loss to decrease. So that's the main idea. If the loss doesn't decrease, you have a problem. So but it's actually very normal that the loss doesn't decrease for the first few steps because you may be using like learning rate scheduler or the model is just like very not ideal. So it's possible that the loss doesn't decrease for maybe a couple hundred steps, but after that it should decrease. Otherwise, the training is not going to converge. So this is something you want to look at. The other thing is that they also log the grad norm here. This is the average size, average magnitude of the gradient of each like training steps. So if this thing is pretty large, it means that your model is getting a very large step of like a update for each like training step. This is sometimes intended, but this should also kind of decrease as your model converges to an optimal point. Because like if the model is getting better, you don't want it to make a very like larger and larger updates. So if the grad norm is increasing, then something is wrong with your like training process. And that's basically it. So I don't think we can go over the evaluation. This is like taking okay, we need another 1 hour for this to finish. So yeah, I think we can go over the how to debug model now.
Great.
And
Yes.
I don't think you would have it.
We'll just maybe spend 10 minutes on it.
Okay. Chanakya, do you want to?
The same slides or?
Yeah. So this is where's my? Yeah, I think this is your slide, right?
So I think the philosophy here is like debugging AI models is more of an art than a science. And that's what we're trying to do here. And towards that, like normally when you code up a program, you have some signal that you get that the program is correct or wrong, right? But in the machine learning model, it's not very clear when your model works, when it doesn't work. So the idea behind this, say this debugging checklist is just so that you have a bunch of checklists that you can go over just to understand what you can improve for your models. And right now, if you haven't trained a model before in your life, this might seem a little pedantic. It might feel very obvious, but I think these things are very useful in the long run. So just to begin with, so training neural networks, it's more of an art, right? It's less to do with some things work and some things don't work. Sometimes your models train, sometimes they don't train. And the idea behind that is, can we sort of demystify this process? And towards that, you have some weird bugs. Sometimes your gradients are very high, sometimes they're very low, sometimes your losses are infinity. And then what do you do with that? That's basically the idea. And this is the recipe. I think this is one slide that covers everything that we want to do. Whenever you want to train your models, we would suggest you look at this first before starting training your models. So towards this, I think this is something David also touched upon, which is you have to become one with the data. As machine learning engineers and scientists, we love trying to use the most fancy model possible, right? But I think that's counterintuitive to what really you need to get good performance.
Can you move the thing so that you can see your moves?
That's the most important. So, having said this, I think that initially you should spend a lot of time just looking at your data, understand the distribution of your data, and seeing if you can come up with your own patterns. The idea is that in most cases, specifically if you're going to train neural networks for your use cases, you won't have a lot of data such as, for these large language models. In that case, you need to come up with models that actually sort of model some patterns or identify certain patterns in the data that you have. And that's the reason why we're saying that look at the data, spend a lot of time just looking at the data and trying to understand some intuitive patterns that you can model. Having said this, like once, sorry. Yeah. So once you've already come up with, once you've already looked at the data and you sort of have some intuitive understanding, try to come up with a very simple model where you can get some signal, in the sense that maybe you come up with a very simple model, it could be linear regression or a simple columnar, and try running that on whatever data you have. In some cases, if you're using like data sets that have already been curated before, there's a very high chance on GitHub someone's tried to solve this problem. So pick up those models, try using those, and then see what happens. And in these cases as well, in Torch, you initially start with something called a random weight matrix, right? Which is essentially sampled from some distribution. Doesn't matter. The point we're trying to make is fix the seed first so that you can understand. So that's a deterministic process. It's not like you have an additional variability there. Having said this, try to like simplify your models as much as possible and always look at the loss at initialization. So sometimes a lot of the time your losses at initializations are infinite. This could be due to a bunch of reasons. And this is a very good cross check to understand if your models are actually working well or not. Finally, the last thing what we would suggest is if your models don't seem to be working very well at all, try to overfit them on a single data sample. What that means is try to make sure your model memorizes what the data is for one single sample, just to identify if the model is capable of learning the data or not. If it's not capable in the first place, then you can go back and start coming up with a better model for whatever you wanted. So I think this sort of like bleeds over from the previous slide, which is come up with a simple model to overfit on a very small training data set. And this is basically what you keep trying to do. And once you do this, see if you cannot reach a lower error rate. If you can't reach a lower error rate, you can go back to the part where you look at the data once again, or you come up with a better modeling strategy for the same thing. And towards doing this, you need to visualize your loss dynamics in the sense that how does your loss decrease, increase, are there certain weird things that happen? And try to also look at your gradients. So sometimes your gradients go up to infinity for multiple reasons. You might not have coded it well enough, or your initializations are not wrong, but you haven't normalized your data well enough. So this gives you some understanding of what you need to fix so that to get your model working. And I think the biggest takeaway is don't worry so much about your architecture initially. I think a lot of times we end up focusing on trying to come up with some cool architecture, assuming that you read some research paper and so on and so forth. But the idea is don't do that. It's sort of counterintuitive to what you want to do. Finally, if you've done all of this, I think one interesting thing here is in machine learning, we don't really care about memorization, we care about generalization. And towards getting to generalization, we need to do some regularization techniques such as dropouts, weight decays, and so on and so forth. So once you know your model does overfit on your training data set, then try doing this. Until then, don't do any of that. And finally, I think I cannot reiterate this enough, that in most cases, your model could be working perfectly well. You just might not have found the right hyperparameters for it. So it is in your best interest to try and search for multiple hyperparameters, specifically if your model is small, just so that you get the right performance. And most of the times what happens is I've seen a lot of data scientists just run the model de facto, and then they get a very bad accuracy or whatever. But if you just train them well enough, you do get like really good results. So try doing this. And finally, once if you've done all of this, use like different ensembles if you want, and try to train the models past convergence, because sometimes that does help. And if you've done all of this, then finally start looking at more complicated architectures, which is something that you can do. So I guess this is the basic pipeline. You obviously focus on the data first, come up with simple models. In those simple models, try to overfit your data. Once you know you can overfit on the data, regularize it, and then fine tune it for whatever downstream performance you want. And I guess this is the rough sketch or the basic debugging tips that we have. If you have any questions, I'm happy to answer them. Just to I think there are two blogs here which we will share with you, and another blog by Ali Rahimi. I think you guys should just go over them so that you get a handle of what we're talking about.
Right.
That's
Folks have any